Yeah. Hi everyone. My name is Brandon. I'm a second year. Wow, it's actually second year grad student. I work at UW Madison in Danny Frederickson's group. We do quite an interesting mix of studies with that mostly involve intermetallic phases. And I think this is just like quite an interesting area of chemistry overall because not many people really do that kind of work. In my spare time, I'm a big fan of vintage hardware. I have a disturbingly large keyboard collection, and I'm a big fan of Formula One. So yeah, that's it. That's a bit about me.
My name's Heidi. I'm now in my third year of PhD studies at Colorado State University, and I'm joint with the Peyton and Mcculloch research groups, but the Mcculloch Group has since moved to Oklahoma State University, but Martin McCulloch is still one of my co-advisors. But yeah, the Mcculloch Group focuses on using molecular dynamics to study biomacromolecules, and the Peyton Group uses quantum mechanics, mostly density functional theory, to study organic reactions. And they also do a lot of chem informatics. Have been starting to do a little more machine learning and things like that. So in my free time, I like to paint a little bit. I've picked up the cello again. I played the cello like in middle school and a little bit in high school. And then I just decided to like buy a really cheap cello and kind of pick that up again. So I've been doing that. And then I have a pet rabbit named Rorschach because he looks like a Rorschach ink blot. And yeah, that's pretty much me.
Hey everyone, my name is Matheus, and I'm a PhD student in Brazil in the Federal University of Pernambuco, and I carry out my research at the Oswaldo Cruz Foundation, which is a research institute from our health ministry. And I work with computational chemistry to study biochemical phenomena, mostly related to protein engineering. So I use computational methodologies to design novel proteins with novel functions. And for that, we use a lot of computational chemistry to simulate the proteins, and we do use a lot of machine learning methods to design novel proteins also. So in my free time, I like watching series and reading some books. So that's it.
And I'm Oliver, the co-host, who's a chemistry student in Switzerland. And Tom, who
what are you doing in your spare
should be
time?
able to hear now. I paint. I do chemistry and physics.
Yeah, Brandon hit us with the what do I do in my spare time fact, and then everyone else.
Yeah.
One.
I mean, I had the two keywords in my hand. I had to show them off.
Yeah.
I do amateur astronomy too.
All right.
Tom, your turn.
What do I do in my spare time? I'm a PhD student nearing third year, which is terrifying. And in my spare time, I play in a band and I play the saxophone and the keyboard.
The music's pretty good though. I like your band, Tom.
Oh, thank you. Oh.
My parents do too, actually.
Oh, we're here at the start.
Let's introduce the field.
Oh, the field, yes. So we're all doing I'm not in the field of computational chemistry, and I may seem a bit out of my depth here. So, what do we need to know before we can get into the presentations? Do we need a quick peruse of the Wikipedia page? I feel like we need, roll your eyes. All right, let's do it. All right, computational chemistry. Is there even going to be a good Wikipedia page?
It's a big field, though, probably.
Uses computer simulations to assist in solving chemical problems. Okay, I mean, that doesn't tell me anything new. Well, okay, I'm never going to get through.
There's no picture in the top right. There's no way we're going to be able to get through this.
I mean, the issue with defining computational chemistry is that sometimes people draw a line between theoretical chemistry and computational chemistry, even though there's a huge overlap between the two.
I would say you could probably divide computational chemistry into 3 different categories, and that's theory development, simulation methods, and then chem informatics.
So where out of those 3 fields do you guys fall into?
I'd say that my field is probably like it's computational structures. Like, so I say it's like simulations of systems, but also we have new theoretical methods of understanding what's going on in structures. So there is a bit of theory development in what we do.
As I design novel proteins, I'm always simulating their behavior. So I guess I would fit into simulations. But we also do develop some methodologies based in machine learning. So we work in the interface of applying methodologies and developing methodologies.
Mm-hmm. Yeah, I'd say same for me too. I do simulations mostly, but the first paper I was on, we developed a method to study something you'll hear about during my talk. But then I would love to, I'm very interested in machine learning, but I haven't actually done any of my research in machine learning, but a bunch of people in my research group do. And so I love hearing about it.
Yeah, I will say computational chemistry does draw people from a lot of backgrounds. People who are into chemistry, but I've also seen people who are like who have their main backgrounds in computer science or just pure math, end up in computational chemistry. So it's a pretty big draw, especially considering the big interest in how many people want to study computer science or programming to at least
Have
some
you guys
extent.
all got chemistry degrees actually?
Yes, I am just my degree was just in chemistry. So
Actually, no. I hold a bachelor degree in chemical engineering. It's not chemistry, but it's kind of close. So I'm a chemical engineer, and I hold a master's degree in chemistry.
Oh, okay.
Yeah, I have a BS in Chem.
Okay, so everyone's a chemist here.
Oh,
How many physicists are there in the field?
You know,
Yes.
I haven't actually seen like from my personal experience, physicists working in computational chemistry. I'm sure they exist, and we do collaborate with them, but I just haven't seen like people who have a physics background come into computational chemistry, in my experience. But I'm sure they're out there.
Yeah, there are a number of people in the Mcculloch Research Group who either did minors or double majored in physics and chemistry. And then there's another like a theory group at Colorado State University who the only like graduate students who like go to that group have a very strong physics background because it's necessary. They do like simulations of liquids and things that like you really need a very significant physics background to be able to start getting involved with.
I know not just physics in the field, but also biologists. My advisor, he's a biologist, and he works in computational chemistry. The people of physics, they are really strong in the field. Since we have mostly of our models, they're based on physical assumptions. So yes, physicists are really important for the field of computational chemistry.
Do you often seek to do this sort of collaboration with experimental, or is there quite a lot of work you think that stands up on its own?
Our group does both computational work on a large scale, but we also do experimental work. So we actually do end up making the intermetallics that we do studies on. Some of us in the group just do computational work. Some of us do a mix of computational and experimental work, and that can vary over time.
Yeah, I think it'd be difficult to find a purely computational group that doesn't have strong collaborations with experimental groups. The Peyton Research Group collaborates a lot with experimental organic chemists at CSU, where we can just kind of run quantum mechanic calculations to study a reaction pathway and kind of give some atomistic inference as to why one isomer might be favored over another and things like that. And so I think it's very common to see things like that.
Yeah, in the field I work in computational chemistry, mostly of the work, they require experimental validation. Our group works with theoretical and experimental, with both activities.
If I say the word quantum, is there like a divide where you say, oh, these people are doing quantum calculations, these people aren't, or is it all kind of like you're dealing with quantum phenomena? That's what everyone deals with.
So in my research, I'd say that pretty much everything we do. So everything we do starts with density functional theory as its basis. So that I would say be considered quantum, even though one of the interesting things, I took a class on DFT recently. One of the interesting things, it doesn't work directly with wave functions. It actually works with electron density, and that's why it's so favored. It actually goes a lot faster when you don't have to toss in the complex numbers. But our entire group either uses DFT, we'll use DFT to get an idea of what our structure is going to be, what our potential energy, what our electron density looks like, and then use those maps to draw conclusions. And I'll show this in my presentation, and we can analyze those maps further.
Yeah, but then on the other side of things, where like density functional theory kind of lies in that quantum realm where you're dealing with like very microscopic, like you care about the electrons primarily and the charged particles, the microscopic charged particles, whereas On the other side of things, you have molecular dynamics, which are more driven by classical mechanics, like Newtonian and Hamiltonian mechanics. And so that's where we don't necessarily care about the motions of electrons, we care about the motions of whole atoms. And so it's a little bit more coarse-grained in that. And the reason for that is not because classical mechanics is more accurate. That's actually not quite true. Quantum mechanics is definitely the most accurate that you can get, but it is very computationally expensive. And that's kind of the thing that like computational people always have to consider is like, how long is this going to actually take to calculate? You wouldn't be able to simulate an entire protein quantum mechanically, or like even using density functional theory in any reasonable amount of time. So you have to use classical mechanics to be able to do that.
Yeah, it like depends on the system you're modeling. So there are many systems you can model, and each of the system has its own particularity. It's a huge system or whether it's a small system. So it depends also in what information you're interested in obtaining. So you can use the Schrödinger equation for calculating electronic properties for small molecules, but it doesn't hold for large molecules such as proteins. So just imagine, you can calculate the electronic distribution for a small molecule like CO2. It has a number of electrons. It's like treatable. But when you go to proteins, it has like millions of atoms and millions of electrons. You can solve you can apply from the equation for each of the electron in a protein. So we use alternatives. We can use classical mechanics, as Hidi mentioned, and there is like other approaches. You can combine both. You can treat the system. Part of the system is quantum mechanics, and part of the system using classical mechanics. So it really depends on what you want and what you want to get, and also what you have.
Will all of you be saying the acronym DFT a lot?
Yes.
This article is, once again, pretty dense. If you had to sum up what DFT is in a couple of sentences, how would you sum it up?
Sure, I'll take a bite out of this one. So DFT is basically a way of treating systems of atoms, and specifically actually their electrons, by instead of solving wave functions directly as we would do for like the Schrödinger equation or for like other computational methods such as Hartree-Fock, we look at the electron density, which has its advantages because we don't have to think about the phases of the wave functions or complex numbers or anything like that. So there's less numbers to deal with, and it's much faster to do that. The density functional is basically, it's a functional, which means that it takes in a function and spits out a number. And the function that it takes in is the electron density, and the number it spits out is the energy. And we can use that functional in various ways to figure out what the ground state or the lowest energy configuration of electrons is for a system, and determine the properties of materials. And we can recover orbitals and other quantum mechanical phenomena through that treatment.
A lot of density functional theories will also include empirical parameters. And so these are just things that are like measured from experiment, and they use that to then kind of make their approximations a little bit more realistic according to what is actually observed in experiment.
So that's pretty suitable for small molecules. But when you go to huge molecules like proteins, there is a certain limitation.
So when we say that we're like running a DFT calculation or like running a quantum calculation, like there's kind of like two important things to consider when you're doing those calculations, and that's what level of theory you're using. That's what we'll talk about a lot. And when we say that, like, at least in my case and Brandon, it sounds like in your case also, we're talking about what kind of density functional we're using, because there are a great deal of density functionals that groups have come up with. And a lot of the like quantum chemistry packages like have a number of them like already installed and working in their software. And so you kind of have to pick from them. And so that's a big decision that you have to make depending on your system, like deciding which level of theory to use, which density functional to use. And then the second part of that is which basis set to use. And so the basis sets are going to be what mathematical formula is being applied to the atoms to describe kind of the electron density around those atoms.
So one of the key, and I feel like is one of the most like interesting findings with like DFT, is that we know that a density functional exists. We know that there's something that will take an electron density and always give you the exact energy for it. but we can't describe it perfectly. It's actually still an open question. So we use these different levels of theories as like successively better approximations to our systems. And so what we use in our group is we usually use LDA, which is just basically treating the electrons like they're kind of like a gas of electrons, but you can make successfully better approximations as you take into account more factors. But that takes more time, or you might use empirical parameters. I actually teach a course in organic chemistry where we specifically use B3-lip as our exchange correlation functional, which is the part that's really hard to approximate. And that works well for his students.
But sometimes, don't you, isn't, let's say, interpretation favored? For example, natural bond orbitals, when you do NBO calculations, there's less physical meaning in there, but it's easier to interpret when it comes to reactivity. Yes,
so actually our students use NBO as part of their as part of the work that they do in their organic chemistry class. And it's a great tool, I think, for them to understand how bonding works, about atomic hybridizations, and why VSEPR or VSEPR, the theory that we often teach students for molecular geometries, isn't actually always giving us the right answer.
All right. Well, I think muffin tin approximation. Sorry, I'm getting distracted. There's no nice pictures on any of these articles. All right. I think we're ready for some presentations. And then we'll have some more questions afterwards.
So here we go. I'm going to give us a brief intro to chemical pressure analysis. And while this is actually quite a fascinating and honestly complicated subject, I think the idea of chemical pressure makes it really kind of makes a lot of sense and brings ideas we've thought of in, I guess, maybe even taking Gen Chem or taking high school chemistry. It kind of makes these more visible, and we can take a look at how atoms interact with each other in a structure. So the research I do is in intermetallics. So let's start off with a really simple question. Let's take two metals. Let's just pick any two metals. So we have sodium. We all know and love sodium. Some of you may have seen it tossed in water. Incidentally, I am not one of those people. I've never seen sodium tossed in water, even though I had a kilo of it sitting around in the glove box I worked in as an undergrad. And it's a pretty simple structure. We have sodium in its body-centered cubic structure. Nothing much to really think about here. And let's take another metal. How about cadmium? It's got its own structure. It's hexagonal close packed. Both of these are pretty well represented among the elements. You usually see either face-centered cubic, body-centered cubic, or hexagonal close packed among different metals. We've seen, of course, maybe in our Gen Chem classes or in our high school chem classes, you can react two nonmetals together. You can put carbon and oxygen, get CO2. You can react a metal with a nonmetal, like you can combust metals in air. You can react them with hydrogen or sulfur or what else. But what happens when we react these elements together? Is there some sort of reaction? And the answer is yes, there is a reaction. There's actually a great video of aluminum palladium reacting with each other. It is a highly exothermic reaction. In fact, the energy density of a mixture of aluminum and palladium rivals that of TNT. It's actually that exothermic. But to answer this question, and let's just restrict ourselves to a relatively limited scope. Let's just look if we have one equivalent of sodium and two equivalents of cadmium, right? There are many different structure types, and I'm just going to represent a few of these here. So here's the cobalt silicide. This is in the fluorite type. It's a structure you might be familiar with if you ever study minerals. We have the aluminum boride type, zone type. We have two Labus phases, which are structures that fall naturally out of the question of sphere packing. If you ever learn about how spheres can pack, you usually see that there's going to be either a cubic lattice, space-centered cubic, or you can see you're going to make a hexagonal lattice, which is the hexagonal close pack lattice that we saw earlier. So the Labus phases fall naturally out of the analysis of what happens. We have two different types of spheres, two spheres of different sizes. So this is an efficient method of packing for them. And you can see that these are actually relatively simple structures. You can find that these are all cubic or hexagonal. This is just a smattering of the different types of intermetallics we can find, but this is representative. So I'm going to ask the chat and actually ask people who are listening to the call right now, what structure do you think sodium and cadmium, when mixed in a 1:2 ratio, forms? Take your guesses. Is it the fluorite type, the aluminum boride type, the magnesium zinc type, or the magnesium copper type?
I don't know. Let's go.
It's okay. I'm leaving you in the dark You'll see why I'm leaving you in the dark here.
Okay. I'll go the magnesium zinc one.
You got any interesting answers in the chat?
None of the above,
And-
according to someone, and aluminum boride, according to another.
Okay, so let's see. Y'all ready to take a look and see what structure we got?
All right, let's do it.
Let's do it. This is what we get when we react 1 equivalent of sodium and 2 equivalents of cadmium.
Whoa.
Trick questions.
Well, actually, if you pick the magnesium copper 2 type, which was represented by scandium aluminum 2, you're actually probably closest to being correct because that subunit actually makes up a portion of this structure. But look at this thing.
The chat is really enjoying it.
This is completely insane. How do you go from these two really simple structures, you know, your good old body-centered cubic sodium and your hexagonal close-packed cadmium, and you get this enormous Samson phase. That's what we call this. And before you think of this as chaotic, keep in mind, this is a periodic repeating structure. This has been solved. Back in 1962, actually, and my PI, Danny Fredrickson, he actually wrote another paper on this, I believe 2008. Why? What gets these two structures to form something that's none of the above, whoever said that was correct, and just end up with this, well, it looks like a mess, but it's actually a highly symmetric and periodic mess. And I will note that there are actually sites where you might see that there is mixed occupancy, where sodium and cadmium may substitute for each other, and where there's partial occupancy, where you may see an atom there, you may not. But overall, this is the structure, and it's pretty well defined and can solve it and describe it. Now, I won't go into describing the structure of sodium cadmium 2 as it is a massive undertaking, though the paper that is cited here actually does explain what goes on and does give a nice paper model, actually, of how to construct sodium cadmium 2. But to get an idea of what might be going on in these intermetallic structures, let's take a look at what factors affect intermetallic structures. And we can think of 3 basic factors. Electronegativity is something that we think of. So, and it tells us like how much atoms want to give up or receive electrons. And this can tell us like quite a bit about what we expect these phases to be. We have some phases such as Zintel phases, which we can describe as being almost like a cation and an anion. So that's what we see when we look at sodium and thallium. It actually is more ionic than we expect, than we think of just by mixing 2 metals together, because we don't usually think of metals as being ionic. But we do see that if we look at analysis, we find that sodium is giving its electron density to thallium. And it is quite an interesting structure type, or sorry, a structure to study from the perspective of electronics and where electrons are going. So that's one thing we can look at. The second thing we can look at, of course, is bonding interactions. So we know that, and this is just a really simple diagram of what happens when you have hydrogen atoms, and you bring them close together, right? You can form a bonding interaction where the 2 atoms will share their electrons, and you can form an anti-bonding interactions where you can think of them as kind of not sharing their electrons. I mean, it is a single wave function, but you can find that there's a nice node in the center where there's a drop in electron density. We know that we want to form as many bonding interactions as we can to form a stable phase. But of course, we don't want to have too many electrons that we start populating too many of the anti-bonding states and therefore increase the energy of our phase. So that's the second factor we want to look at. Those 2, electronegativity and bonding interactions, both fall under like the electronics domain. But if you've taken organic chemistry, you might be aware of steric factors too, and those are very much at play here. We think of it as in terms of packing strength. Atoms are all competing with each other in terms of trying to bond with each other versus trying to repel each other, because while the nuclei and the electron clouds attract each other, the nuclei of 2 atoms repel each other, and the electron clouds repel each other both through electronic factors and through Pauli repulsion, because you don't want to put 2 electrons in the same state, and that's just not allowed. So when we have an atom that is coordinated by other metal atoms, they're all going to try to come close enough to the central atom so that they can bond with it, but they don't want to be too close to each other and have a large amount of repulsive interactions, because that would make it a less stable structure. So we have these 3 ways of looking at our intermetallic structures, and really any chemical structure. This is very much true for organic molecules, proteins, etc. These things all go on. Now, our group has ways of looking at both electronic and steric effects in intermetallics. But the one I'm going to focus on today is specifically the pole packing strain part. And we have a tool that we use, and it's called chemical pressure. And it does what it says on the tin, though the process is a bit complicated. And in these next 2 slides, I'll quickly run you through how we go from a crystal structure of a intermetallic phase and get an idea of what the pressures look like on each atom. So with chemical pressure analysis, we actually start using Abinit, which is it's a free computational chemistry package that you can download and compile on your computer, commonly run on clusters. We do that here at UW. So what we do, and this is usually the first step with any sort of DFT or any sort of really computational chemistry calculation that has things at equilibrium, is we try to find the equilibrium geometry. We want to try to make sure there's no forces acting on the unit cell, because of course, if there's forces acting on the unit cell, that'll alter the numbers we get and the pressure map that we get, which is bad. And in general, even if you're not looking at pressure specifically, you want to make sure the atoms are all staying in place and the unit cell doesn't want to expand or contract. So we first look at the equilibrium geometry. Then we use a bit of physics, and I think you might have covered this if you ever took some basic thermodynamics. So we know that a system will have a pressure and a volume, and that pressure-volume relation will determine the energy of the system. What we know is that if we make a change in volume, we will get a corresponding change in energy. And the constant of proportionality for that change, and we can think of these as very tiny changes, is going to be P, the pressure. Now, by doing a little rearrangement of the math terms, we can move this around so that we can solve for pressure. And we define pressure as the derivative where there's a change of energy over the change in volume. So in order to get an idea of what the pressure is in a unit cell, we're going to have to look at both the expanded and the contracted unit cells. I mean, in theory, we could look at just one pair and get an idea of what the pressures are, but generally better to look at both and see what the difference is between the contracted equilibrium and the equilibrium in the expanded cells. So with those three, we can actually put together a data set of what we'll know what the potentials are, like the electrical potentials generated by each atom. We'll know what the electron density is from a DFT, and we know that if we multiply the electrical potential by the electron density, or equivalently a charge density, we get the energy density at that point at that point in space. So then we get a map of the energies inside a unit cell, and by looking at the difference in how that energy changes within like a unit of space inside that unit cell, we can then get a map of the pressures inside the unit cell. So you have to divide the space up. You can't just look at the entire unit cell, because the unit cell at equilibrium doesn't experience any pressure. But internally, if we look at individual units of the unit cell, like we break it up into a grid, then we can see what goes on inside the unit cell in terms of what the pressures are like, and also what the energies are like, though, of course, we use the energies to calculate the pressures. Now, we can look at the CP map directly, this chemical pressure map, but one thing that's really useful is to think about how different atoms experience this pressure. So let's say we want to look at a specific atom in a unit cell, right? We can try dividing up the unit cell in different ways, and this is where things can be a little arbitrary, in the sense that there is no single way to assign volumes to atoms. But one of the simplest ways is to construct Voronoi cells. And Voronoi cells are basically the regions in space that are closer to one particular point than to any other point that's defined. So in this case, this is what the Voronoi cell of this central atom looks like. Kind of like a dodecahedron, but it's got some other faces. Not exactly. It's a bit out there. But this whole structure, like this whole space, we can assign the pressures, like the regions of the pressure map, to that particular atom. So those are the pressures that atom experiences. Now, there are different ways to divide up the cell. We can actually use something called Bader charge analysis to divide up the cell, not by just which atoms are closer together, but by how much electron density is assigned to that atom. And we get slightly different pictures of chemical pressures. We can verify which chemical pressure map is the most accurate by looking at the phonon modes, which is the modes of collective excitation, so like the vibrations of the atoms in the structure. And some of these will correspond more neatly with phonon modes than with others. Though as of yet, that is not a calculation I have actually done yet. So that is something that I won't really be going into too much, but know that we can match these chemical pressure maps to what actually goes on inside the unit cell. Now that we have this idea of what goes on and how we get these chemical pressures, let's take a look at an actual system, or actually an actual set of systems, and see what chemical pressure can tell us about these particular systems. So the first thing that I'll just note is that in a chemical pressure scheme, we'll see black lobes and white lobes. Black lobes are going to be regions of negative pressure. You can think of it as a black hole. And white lobes are regions of positive pressure, which means that they want to expand and push things away. So a group of systems that our group wrote a paper on back in 2014 is the calcium copper 5 type systems. This is a commonly represented intermetallic. In fact, you may have encountered an intermetallic of the structure type before, because samarium cobalt magnets are composed of samarium cobalt 5, which crystallizes in this particular structure type. And it's well represented among intermetallic structures. However, we find that calcium palladium 5 also forms, as well as calcium copper 5, and you can get an idea of what it looks like. Here's the red calcium atoms in the center, and then we have two different layers of copper atoms in calcium copper 5. And the blue layers are what we call cogomanets. They are just 6-pointed stars, and they are a repeating pattern over space. We find that calcium palladium 5, and we're omitting the points of the cogomanet, but we can see the hexagonal interior of the cogomanet in this particular view. We can look at this chemical pressure scheme for calcium palladium 5, which is a known structure, and we can see that calcium experiences some negative pressures that are pulling it towards this upper hexagonal ring of atoms, or the upper part of the cogomanet, but also the lower part of the cogomanet. So this calcium atom would like to be closer to either the upper or the lower cogomanet, but right in between, it's at an equilibrium, it's at a balance. Now it turns out calcium silver 5, and if you can think about it, so it's 1 over on a periodic table, so it's a little smaller. Calcium cadmium 5, which is another step over, and again a little smaller. Neither of those exist. And if you look at the chemical pressure map, we can see why this is the case. It turns out that calcium, which already has these big negative pressure lobes, just experiences more and more negative chemical pressure as we go on with our, as we go down the periodic table into smaller and smaller atoms. We don't see calcium silver 5 at all. We don't see calcium cadmium 5 at all. And you can see that this unit cell experiences a lot of negative pressures all pointing towards each other. So this unit cell kind of wants to just cave in and collapse on itself. So what we can look at though is, first of all, do calcium and silver form any sort of intermetallic? And the answer is yes, they do. But it's not calcium silver 5. We see a different intermetallic form in this phase, and it's actually calcium 2 silver 7. So we can see how this whole transition takes place. Or you can think of it maybe not as a transition, but just like why the calcium 2 silver 7 structure is preferable to the calcium silver 5. By the way, I don't know if I've said aluminum in the past, but it's definitely calcium silver. Calcium silver 5 can relieve this big negative chemical pressure by bringing these silver atoms closer to itself. And in the structure, this is accomplished by first deleting this entire layer of silver, this entire silver hexagonal layer. It's just removed from the structure, like we did, when we see it. But also we shift this second, like we can break this up down to 2 separate layers. We shift these over a bit so the 2 calcium atoms aren't getting too close directly. And we move them so that the silver atoms on the hexagonal, or in the hexagonal ring around calcium, can interact with neighboring calcium atoms. And you can see that the interatomic distances are reduced. We go from over 3.5 angstroms, 3.56 angstroms, to 3.14 angstroms. And this basically, what this negative pressure lobe is telling us is that there's a bonding interaction between calcium and silver that wants to form here, but these structure types just keep them too far away at equilibrium. So we can't actually observe either the calcium cadmium or calcium silver phases, but we do see a modified phase that is similar to both, but has a slightly different arrangement of atoms. So if you were to take, and we do this in our group, we will make intermetallics by taking 2 metals, putting them in an arc welder, giving them a big bolt of electricity, and then they will form intermetallic phases, which we can then crystallize in an arc furnace and then solve using X-ray. Using an X-ray diffractometer. And so what we find is, even if you have one equivalent of calcium and 5 equivalents of silver, what you end up getting is primarily this calcium 2 silver 7 phase. And you might get some either silver-rich phases or just pure silver left over in the reaction. And speaking of which, calcium-rich phase. Happy Spooktober, everyone. Now, one thing that I want to talk about, and I think that was like a great instructive example of what CP can tell us about structures. Another thing I want to talk about, and I feel like may not be something that a lot of people think about when discussing computational chemistry, especially because this isn't something you think about at a high level, is how we do computational chemistry. As I mentioned a little while ago, I teach an organic chemistry class where we use WebMO, which is software that allows students to build and manipulate structures in 3D space and view and visualize the results of these calculations quite easily, and it's a very user-friendly interface. Unfortunately, the software that we use, ABNet and VASP, they are not supported by WebMO, and so a lot of our calculations are done through a terminal. So we log on to Phoenix, which is the computational chemistry cluster over at UW-Madison. We also have a separate cluster, Sunbird, that we use for classroom calculations, and Starling, which does cool GPU stuff. And we log into this cluster using OpenSSH. The way this arranges, there's a head node that controls all the rest of the nodes, and we submit jobs to other compute nodes, and they take care of the calculations for us. Or you can also interface directly with the compute node and log into it and run a job there yourself instead of just telling a submission script, hey, here's what I want to do. So the way you do this and the way that we have it set up is we usually have some sort of Unix-like environment on our computers. So our group mostly uses Cygwin. I'm the black sheep that uses, I've been testing and trying out the new Windows subsystem for Linux. We use OpenSSH to connect to our clusters, which is something that comes with pretty much any Linux distro, and lets you just log into a computer and interface with it. You pick your terminal emulator of choice, Windows Terminal, and on the cluster you get your software. And while there's a wide variety of software, because there are plenty of different research groups that do different types of research, the main two things, like the main two big software packages that we use are ABNet and VASP. ABNet we use to run our group software CP package, which is how we got the results, the computational chemistry results. We do another type of calculation called reverse approximation molecular orbital calculation, and we use VASP to do that calculation. It gives us an idea of bonding in terms of, like, instead of looking at the big, like, plane wave basis of DFT materials, we can look at actually more orbital shaped things and see individual interactions between solids. We use VASP, we get results from VASP, and then we use a DFT ROMO package to get an idea of what the orbitals will look like. And similar for CP package, we get our results in ABNet, and then we transfer those data sets into CP package, which will do the number crunching and tell us our pressures at each site. So that's something that we use. Another thing that we'll use, and I'll point out, is that we use a lot of Matlab. Some of the figures that I made for this particular presentation and some of the ones that have been made for the papers that we've talked about have been made in Matlab. We have our own figure tool that we use to generate figures, project data. This is just a screenshot of me generating one of the figures for this particular presentation. Want to get a little meta here. But we also use software like Vesta and Diamond, which we use to take a look at crystal structures, and we can start drawing bonds and showing links between different parts of the structure, add or remove atoms as needed to show different portions of it, because we don't always just look at the unit cell. We look at how different atoms are attached to each other, and on long distance relationships that between things that might go beyond the unit cell, or when you have a big unit cell, things that are short distance, and you want to get focused on, especially for like crazy structures like sodium cadmium 2. As a quick acknowledgement, I'd like to thank everyone in the group, because I would not be able to give this presentation without the vast amount of knowledge that our group has provided me in terms of understanding how to calculate CP chemical pressures, in terms of how to get great figures. I especially want to thank Erdon, Kendall, and Amber for that. They have been incredibly helpful. And of course, Danny, for making this entire, doing research on intermetallics possible, and having an overall awesome group with a bunch of friendly people. If you want to know more about the research we do and what we work on, first of all, we do have a Twitter account that you can follow. Our group has a ton of very artistic members, so chances are you will see a good amount of interesting content. For example, our chemistry department publishes a zine, so there's input from everyone in our department, including especially our group members. We just have a ton of great artists in our group. Unfortunately, I'm not one of them, but I try. And I will also point out that we have a group website, and while I didn't make a slide on this part in particular, we do have 2 tabs on the website that I think might be useful for anyone who is interested in learning more about solid state chemistry. We have a tab on interactive solid state chemistry and on science through comics. Our artists are also great at drawing comics, and we have comics about different elements, intermetallics and what they are, and forces in their structures, why we see the structures we do. This is still also a work in progress, so definitely come and check back on our site if you ever want to take a look and see what we're updating, because we've got some interesting new things to see in the future. So that is it for my presentation, and thank you everyone in the audience who's watching, and I hope you enjoyed that.
Thanks
Thank
very
you.
much.
We've got some questions from the audience about how you confirm your calculations experimentally.
So what we'll try to do is we'll actually try to take, like, we'll think about like different pairs or groups of metals. Like, for example, we want to look at a binary phase. We want to say, hey, can we make this structure type? And granted, a lot of this is well known through phase diagrams. So binary phases are generally not as interesting as, say, ternary phases. But then we'll take some amounts of each different type of metal, and we'll actually try to synthesize a different phase in an arc welder. So the question then becomes, once you arc weld these metals together and form an intermetallic, what crystals do we get? So we heat it up in a furnace, and that usually actually goes, we heat it up and cool it down slowly, we tend to get pretty nice crystals of our intermetallic. And then we do a structural study and through X-ray diffraction, and we see what new crystals we can get. And this can be kind of this is not a process that I'm doing personally, so I can't say too much about how this differs from, say, like small molecule or protein X-ray crystallography. Other than we do get a lot of very interesting like structures and like space groups and stuff.
There's another question about how do you know that the instability of the intermetallic is due to the chemical pressure and not other effects?
Right. So there are actually like multiple effects, and sometimes you'll see that the chemical pressure scheme will look totally okay. Like there won't be any particular instability in the structure. The pressures might be very low. They won't be unbalanced, and you'll find that the chemical pressure scheme doesn't say anything about why this system is not stable or why we see this unusual structure type. When that happens, then we can safely say then chemical pressures aren't really telling us much about why this system doesn't work. So in that case, we probably will turn to electronic effects and see how that what picture that ends up giving us. Because a lot of what we see in chemical pressure schemes is due to basically the radii of the elements. And so you might have two metals that end up having a perfectly fine difference in radii or ratio of radii to form a certain structure type. But maybe if you take two similar metals that have that same ratio of radii, they just don't have the electron counts to support that. So we end up seeing a different structure type for electronic reasons. So if there's no packing issue, CP will tell us that.
Are there cases where you have really strong chemical pressures, but they're balanced out, so the intermetallic is actually stable?
Yeah, so actually, and this was in the presentation, like one of the things that's a little interesting about chemical pressures is they can vary actually quite wildly between different elements. Like you can find, and usually this goes as you go down a periodic table, you'll find chemical pressures that are in the range of tens of gigapascals or even less than like 10 gigapascals per atom, like the overall net pressure on the atom. The difference in pressures might not be enough to compensate for that. Or meanwhile, you can find things that can have thousands of gigapascals of pressure, and yet they're all balanced out. So it's less about the magnitudes of the pressure and more so about how they're balanced out. And when we plot these different data sets, we'll often just scale them to see so that we don't really, we'll have a scale bar there to get an idea of how big the pressures are. But the key thing when looking at a CP scheme is whether the pressures are balanced.
All right, great, thank you.
All right. Thanks for the presentation.
All right, well, I'm excited to talk about my applications of molecular dynamics and quantum mechanics to study allosteric activation. We'll get started with this. All right, so allostery occurs when a perturbation at a site distant from the primary active site influences protein function. I like to liken this to the butterfly effect, where small events can have large, widespread consequences. So you can imagine this blue butterfly here, which represents the allosteric modulator, also known as the effector molecule, is naturally attracted to this vibrant flower, and that causes it to gravitate towards it. And after it lands on the flower, it causes a change to occur over a distance away in the system. This change, highlighted in yellow, occurs at the primary active site, nominally known as the orthosteric site. This effect could change either the binding affinity of the active site for the natural substrate, or it could lead to structural changes in the active site that affect the rate of the reaction. This macromolecule shown here in white and orange is imidazole glycerol phosphate synthase. I'll be calling it IGPS for short. It is a fairly well-characterized allosteric system that I've been studying. For IGPS, the allosteric modulator is called PREFAR, shown right there. And when PREFAR binds, the reaction that occurs in the white subunit is increased by 4,500-fold. So it just has this really incredible catalytic dependency on the allosteric modulator. All right, so why should you care about allostery? There are a few reasons, but I will touch on what I'm most interested in, and that's the rational design of allosteric drugs. Traditional drugs are designed to target a system's orthosteric site, but more recently, attention has been given to drugs that could target these allosteric sites. In 2019, Allostery made the cover of CNEN with the main article explaining the benefits of allosteric drugs, which have led many pharmaceutical and biotech companies to invest time and effort into this area. Dr. Aaron Fenton, a collaborator of the Mcculloch Group, who has done really great experimental studies to characterize allostery, refers to it as the second secret of life, behind the first secret of life, which is essentially the genetic code and the central dogma of biology. One advantage of allosteric drugs that allosteric drugs have over orthosteric drugs is better specificity for the target, which could reduce off-target side effects. Another advantage is that allosteric drugs have more fine-tuned effect, whereas orthosteric drugs are in competition with the natural substrate and are designed just to inhibit the function typically. In this sense, allosteric drugs are more like a dimmer light switch rather than orthosteric drugs, which are more like on and off binary switch. Allosteric drugs typically have a continuum of effects, whether that's a positive increase in activity or a decrease in activity. And this could also mean that we can start thinking about designing drugs for targets that have been previously termed undruggable because we couldn't target that orthosteric site for one reason or another. So what actually are we studying when we study allostery? Well, first, we need to get a better handle on the foundational components of allosteric regulation. At a minimum, allostery involves the interactions that occur at the binding sites, which are shown here in pink and green, and also interactions that occur between these two binding sites. And this is nominally called the allosteric paths. And so first, I'm going to be talking about how we study these allosteric paths. In the Mcculloch Group, we demonstrated that the covariance matrix is the observable of interest in structural allostery, and that it is the Hessian that should be used to describe signal propagation between the two sites, those allosteric paths. The workflow is as follows. We simulate the system. Here we chose IGPS, and we do this by simulating all of the atoms using molecular dynamics, which uses Newtonian mechanics to propagate all of the atoms forward in time. To give you some idea of what MD simulation is like, IGPS is kind of like a medium-sized protein. It has 453 residues or amino acids. And it took a little over 2 weeks to simulate 1 microsecond of motion. Right now, molecular dynamics is greatly hindered by computational expense and being able to simulate a reasonable amount of these biological systems. But after we do the molecular dynamics, we then have this insane amount of data. And from this data set, what we do is we extract the pairwise residue covariance to compute what we call the effective Hessian. And the Hessian is nominally the second derivative of potential energy with respect to position. But for this application, it is directly related to the inverse positional covariance, which not coincidentally at all is our allosteric observable. So finally, we then can use the Hessian to identify allosteric paths and compute what we call this sensitivity metric. And the results from these metrics qualitatively capture experimental mutagenesis data on IGPS. So in the paper that we published earlier this year, we explain more about how this theory was developed and what advantages the Hessian provides, including an intuitive picture of how mutations can perturb the system, whereas mutations change the effective spring constants between the mutated residue and its surrounding contacts. And this point is the motivation for this sensitivity metric, which is the derivative of the covariance between active site residues with respect to changing that spring force constant and therefore changing that residue's contacts with other residues in the system. And the next project that I've been invested in looks at interactions at the active site that occur as a result of the allosteric effector binding. In essence, like, what is the actual allosterically active conformation? So as a reminder, when PREFAR binds, this causes a 4,500 increase in catalytic activity. This image is flipped from the first image of IGPS I showed, so keep that in mind. But PREFAR comes and it binds in this cyclase domain on top. And then over 25 angstroms away, the glutaminase activity in the orange subunit is affected. The reaction that occurs in this subunit is the hydrolysis of glutamine to form glutamate and ammonia. And it's this reaction that I'm modeling quantum mechanically. So my hypothesis is that there are structural differences that occur in the active site, in this glutaminase active site, that influence the effective energy barrier of this reaction, and that this is something we can measure using quantum mechanically influenced approaches, such as density functional theory. The workflow for this is as such. I develop cluster models of the active sites from crystal structures with and without PREFAR bound. Luckily, these crystal structures already exist. Next, the next step is then to generate the reaction profiles. And so in the cluster approach, initially designed by Sigban and Himo, it requires some atoms to be frozen in position such that the active site generally remains its active site structure. And so what I did is I froze all of the alpha carbons, and then I let the side chains of the amino acids be flexible and move about. After performing the quantum mechanical calculations, we can calculate the theoretical rate using the Eyring equation and compare that to experimental value. And then the last step is to make chemical inference at the atomistic level as to what is causing this increase in reaction rate when PREFAR is bound. I have a few theories as to what's causing this, but I'm not quite ready to show those results yet. But I do expect to publish on that within this academic year. So stay tuned if you're interested. But that's all I have for today. So first, I'd like to thank Tom and Oliver for inviting me to talk, and I'd like to thank all of the members of the Peyton and Mcculloch research groups. And let me know if you have any questions. You can find me at any of these, through any of these means. But in summary, I hope that you took away that Allostery is like really cool. I think it's really cool. I hope other people think it's really cool. And that we're still in the process of better understanding the foundational components of this phenomenon, and that computational approaches are particularly primed to study allostery due to the atomistic detail and ability to design toy systems to test different ideas. And then if you're all interested in some of the kind of foundational literature on allostery, I have a public Mendeley page that you can visit to read a little bit more about it. But yeah, thanks for your attention.
Thank you. Someone's
question.
asking if these calculations are in solution. Sorry, Tom.
That's right. Are they in solution? Is that, or
Yeah.
they're from crystallographic data? So are they like, yeah, the kind of solution stuff, right?
Good question. The molecular dynamics simulations are done in solution, an ionic solution of like 0.1 molar, which that is what experimental data was done in. So that's why. But for the QM calculations, so far, kind of my protocol, my more specific protocol for that is to optimize the structure of the active site in gas phase first. And then once I have that optimized structure, then I'll do what are called single point calculations in solutions of different dielectric constants, just because the active site is pretty large. It's a little over 150 atoms, and to model that quantum mechanically takes a lot of time. So I first optimize it in gas phase just to get a better idea of what that optimized structure looks like, and then I'll go ahead and optimize it in solution.
Tom, what did you want to say?
When you say, oh, run it, you know, like, what are you running this on? Like, is it a big, like, supercomputer, or, you know, what's, like, when it took 2 weeks, like, what's doing that 2 weeks of grinding work?
Yeah, great question. So we have a local cluster at CSU that I have access to. And so for the molecular dynamics, those were run using a GPU. So you typically think of GPUs for gaming, right? But for a number of molecular dynamics software, you can have GPU enabled like math algorithms that will propagate the system in time, and that greatly speeds up the calculations. If I were to run it on a CPU, which all of the QM calculations are run on CPU cores, if I did that with the molecular dynamics, it would take even longer. But so right now it is like, it's going like significantly faster than what has been done in the past. But yeah, so the MD stuff is typically done on using GPUs, and all the QM stuff, I actually have access to Summit, which is a huge supercomputer cluster in Boulder, Colorado. And so I ran those with the Gaussian software, which you do have to get a license for, and it's pretty costly for different universities, but ASU has a license for that. And so that's how I run the QM calculations.
And when you say the access to a cluster, so that's like a big room full of like servery looking, just air conditioned room.
Yeah, so access as in virtual access. So as Brandon was mentioning, the whole open SSH, that's what I do. Like I essentially sit at my computer all day working on different computers virtually.
Right.
I actually do have a question.
All right, Brandon.
Is there a way you can do your calculations for you? I mean, has your group ever done anything to like can you is there a way for volunteers to run calculations for you, or like pulling at home? Is that something that's ever that's available to y'all, or is that something, are you required to do your jobs on your own clusters, or is that something that's ever been looked at actually, just in general? That's kind of broad.
What do you mean by volunteers to do the calculations?
So probably like folding at home will let you basically save use your unused CPU cycles to solve problems, and say like folding at home will look at problems in protein folding. So is that something that you would ever have access to?
It's kind of like it's crowdsourcing computational power.
Yeah.
If you've never heard of it, then you're not using it. It's fine.
Sorry, I'm unfamiliar.
Yeah.
Yes, that computer in the back is running folding at home. So.
Yeah. Yeah, it's like from chat. It's like Bitcoin mining, but for a good cause. Yeah, basically.
So like using the computational resources that aren't being currently used.
Yeah, so it divides up the computational work of solving whatever molecular dynamics of a protein, and it gives like small amounts to each computer, sort of globally.
Oh,
it's
I see.
All right, thank you. I think it's Matthew's turn now.
Well, I guess my job here was made easier due to the presentations before me. So I'm going to talk a little bit about how computational chemistry can help us to do some protein engineering. And actually, what's protein engineering? So just to summarize what came before me, we can see that not all chemists wear white coats. Actually, I don't wear it since I graduated from my bachelor engineering. So as you can see, we can use computers to model systems and to understand the structure dynamics and thermodynamics of those systems. And for me, one of the most impressive prediction power of computers, like it's undeniable that the emergence of computers in the 1940s has changed the course of science, is that now you can use computer to make predictions before you go to the experiments, and it saves a lot of laboratory costs. Be it will save time or it will save money. If you can rationalize your experiments using computers. And that's the idea that I use here to do some protein engineering. So just before going to the protein engineering stuff, there is a quote that I really like, which is that molecular modeling is the science and art of studying molecular structure and function for model building and computation. And as Picasso said, art is the light that helps tell the truth. So yes, actually, when you use a model in science, that's not true. It's a lie, but it helps us to understand the universe and help us to understand the systems. So when you think about molecular modeling, what we're doing here, like in modeling science, we build a model, a mathematical model, and use computers to solve the equations that describe this model. And as has already been stated here, the modeling level that you use will depend on the size of your system and what properties are interested. Whether it's electronic, atomistic, microstructure, microscale, you can simulate anything you want, and you can use different tools to simulate what you want. And when I'm thinking about proteins, proteins are huge molecules from the point of view that there are many electrons, so it's not interesting to use electronic models to model a protein. So we use an atomistic approach. And when you think about modeling biomolecular systems, atomistic approach is the most widely used. And why am I interested in modeling proteins? So, well, proteins, they are found everywhere in our body. And proteins, they carry out many functions in our organism. So proteins, they contract our muscles. Proteins, they transport oxygen in our blood. Proteins, they made up our muscles and hair and everything. So you can find proteins everywhere in our body. In such a way that proteins, they are the primary agents of biological functions. And just to contextualize with the current pandemics, that everyone, I guess, is aware of the coronavirus thing, but we can blame the coronavirus situation for one thing. We can blame the proteins. What happens in a macroscopic level, macroscopic scale, is nothing more than driven by a molecular level situation where we have proteins start binding. And this binding of proteins is what allows the virus to go inside the cell, is what allows the clinical complications, and this is what allows the pandemics the world is living today. So yes, we can say that the fault is on proteins. So when we think, since this is a molecular protein-based phenomenon, we can visualize the coronavirus situation in terms of proteins. So here we have the human cell, and in human cell, we have ACE2, which is a protein, is a receptor in human cell. So when the coronavirus targets the spike proteins, this protein in red here, when it binds the ACE2, it undergoes a conformational change in such a way that it enters the cell. So you can see again, the fault is on proteins. So what if we could design, if we could engineer proteins for a specific purpose? I mean, we could design proteins that bind the coronavirus surface, that binds the spike protein, and it will prevent the virus entering in the cell. So what if we could do that? I mean, is that possible today? We know that our organism can do it very effectively. Our organism can produce natural antibodies to target those proteins. But some latest results showed that we are not sure of how long our antibodies last in our body. That's one point. And if you want to buy antibodies and if you want to use natural antibodies, that's really expensive therapy. So could we could propose a protein that can bind the coronavirus so that it prevents the virus entering in the cell? That's the basis of the viral neutralization of coronavirus. So yes, we actually can do that, and that's been already done for a long while. And we can do this using two approaches. We can do it this. We can use an empirical approach. We go to the wet lab, we wear the white coat to do this, and we generate random sequences. And it must be noted that the Nobel Prize in 2018 was given for this random mutagenesis process of protein engineering. But we can also do this rationally, where we can use numerical computation and molecular modeling, in principle of thermodynamics, of course, to design a novel protein. So this is basically what we do. We have a structure of a protein, and we want to modify it. So I know that the function of this protein is related to this loop here. So I want to change the function of this protein. So I can just cut this loop and graft another loop, a desired loop. So that I can do today using computational approach. And now I have a new protein, and now it will have a new function. And we did this all using computational models. But what's the drawback of doing this? We know that proteins, they are they are composed of a linear sequence of amino acids, which are small molecules that they join together to build up large molecules that are the proteins. And each protein will have a specific amino acid sequence. And each amino acid sequence will give a protein a unique three-dimensional structure. And in nature, we know that you're going to hear a lot of this from computational chemistry, the word energy. So the three-dimensional structure of a protein in nature is the one with the lowest energy. So if you want to design a sequence, I mean, I want to propose a sequence to target the coronavirus protein. Then I need to design a sequence, I need to propose the amino acid sequence that will result in a structure of lowest energy. And here we have a potential energy surface where each peak of this, you have a protein sequence, a protein structure you can visit. So there are many, many, many possibilities of proteins we can design. And how can we do that using a computer? I've got this video from David Baker from University of Washington that basically he developed a program called Rosetta. And basically what this program does is to use combinatorial mutations to identify which amino acid sequence will yield the lowest energy structure. So you do this randomly. You just change the amino acids in the protein randomly until you find a protein that will have a low energy state. And as I told before, all we do here are models. And to account for this energy, to calculate this energy, we use simple atomistic models in which we consider each atom in the protein as a ball connected with a spring. And we can calculate all the interactions. For example, if you have an atom that's negatively charged and a positively charged, they will interact with each other. And this can be modeled using Coulomb law, which we learned in high school. So yes, we can use potentials, mathematical functions to describe the energetics of a protein. And once we have described the energy of a protein, we can calculate the forces that act upon each atom. And then, I mean, let's suppose I found this protein is the one with lowest energy. And I want to know if this is really a good protein. I mean, is this protein going to fold properly? Is this protein stable? Is this protein soluble? And all of those information, I need to do the experiment to know, but I also can do a computational experiment. I can use the molecular dynamics simulation, which I mentioned before. And those simulations, they can capture the behavior of biological macromolecules in full atomic detail. So that's like a microscope. And using the molecular dynamics simulations, we can connect macroscopic properties and microscopic properties using statistics. That's the base of thermodynamic statistics. So from the behavior of the macroscopic components, you can look at the macroscopic protein, you can infer the macroscopic properties. So for example, here I brought a little video where you can see the protein moving. So the motion of this protein is derived by the interaction. So we have a charged atom and need to attract or to repulse. So it depends on the nature of the amino acids in your protein. And we can infer a lot of information. And we can also infer how does this protein will bind to its target. I mean, I have to design a protein that will bind the coronavirus. Okay, but how can I know that it will really bind? And we can study using the simulations how the protein interacts with another protein, or it can interact with a small ligand. So here's an example. You can see the ions and you can see the ligand moving and the protein moving in the interaction. So that's all. So those are information you can obtain using computers. And ultimately, I can use those information to improve my designs. So, okay, the software gave me a sequence, gave me a protein of lowest energy, but does it bind the target? And I can use simulations to dissociate two proteins and calculate their bind energy. So I can know if they bind tightly or not. And then I can propose mutations. I mean, here we have amino acids interacting, but I want to optimize this interaction. So I can replace an amino acid by another, and I use those simulations to see if it enhances the affinity or not. And I can compute the free energy profile and identify where I can change or where can I not change. And ultimately, it might look easy, but actually it demands many calculations. And as it was mentioned before, it must be performed on supercomputers. So a conventional computer may not be suitable for doing those calculations at a high throughput level. And I would like to take this chance to acknowledge the Brazilian supercomputer that we have, the Santos Dumont, which is located at Rio de Janeiro. I would like to thank you all for your attention, to thank for my research group, and thank you again.
Let's see if there are any questions from the chat.
That's a cool looking building with the supercomputer in it. Yeah, look at that.
The first,
Cool.
the top one's the outside, and the down one's the inside.
And when you look at proteins, like I know one of the problems that you have is that you have a lot of local minima of different protein conformations. To what extent are you searching for the global minimum, or like the lowest energy conformation a protein can fold into? Is that a really important question for you? Is that something that is less relevant, I would say?
So if I understood well the question, when we do those calculations, we generate millions of proteins, like we generate 5,000 millions of proteins, or a million proteins. So we need to filter from those which ones possess the lowest energy. It doesn't mean that the one with lowest energy will be the best experimentally experimentally. So we need to do a molecular dynamic simulation to find the global minimum of the protein and to see if it's stable or not. So we do molecular dynamic simulations to obtain this information.
Shall we move on? Shall we go to some general questions?
You can stop showing your screen now.
Question is, you guys do a lot of coding, right? Like most of the stuff you do is coding.
I would say no, actually. You can actually run, for example, with my software, you can run Abinit and CP package. The worst thing that you'd have to do is compile it, I would say, because a lot of times we'll want to do system-specific optimizations to our software. But generally, even still, like a lot of good software packages will have a build script built into them. And what you'd have to do is just compile the software onto the system you want to set it up to. And this is like from basics, and usually this is already done for you. And then just run the software. And most of the problem, I say, most of the difficult part is getting your input file correct for your software that you want to use. I cannot tell you the sheer number of jobs. I wonder, because on Phoenix, our cluster, we're at about 3.5 million jobs that are submitted to the cluster. I wonder what percentage of them were people just constantly submitting a job that had something wrong with the input file and was just rejected immediately. Like, that's the challenge. Get your input file right.
To analyze the molecular dynamics data, I'll write pretty quick Python scripts to be able to abstract or extract certain numbers from the output file from the molecular dynamics simulation and then compute whatever quantity I'm trying to look at.
And mostly of the software package we use, they are pre-compiled, so you don't have to code them. But as Hidi mentioned, sometimes you need to do some scripting, to do some codes, to do some specific analysis. In my case, as I told you, I generated about 500,000 proteins. And you need to filter them. And to filter those proteins, I have been using machine learning, which has needed a lot of coding to select which protein is good or which protein is not good. Because all those proteins I designed and test them computationally, they go to the experiment. So we don't do only the theory, but also the experiments. We need to validate to see whether a protein will bind to the target or not.
At what point do you kind of say, did you sort of do the bachelor's and then look at postgrad and say, oh, I want to do something computational, I
don't know.
learn how to code?
We have quite a lot of computational chemistry here.
All right.
Quite early,
we did some. And
yeah. UW is actually good at, like, we don't give them the whole logging the terminal and set up your program kind of stuff, but we give them WebMO and can show them like how we can use computational chemistry, and they know the basic steps, like you need to optimize your structure. There are different jobs, different levels of theory that we don't go too much into that part. And I just will quickly append my answer that I said earlier, just because it's being more complete. You don't have to know coding in order to do computational chemistry, but it is extremely helpful.
Yeah. When I started my PhD program, I did not do any coding at all.
Same.
I did all experimental work during undergrad. Like, I think it's not very common to do computational chemistry during your undergrad. And coming in, like, that was definitely like a big fear of mine. I was like, I don't know. Like, I knew that I was interested in like physical chemistry and more of the theory side. And so I was worried that like advisors wouldn't want me because I didn't know how to do anything in Python. And they're like, you'll learn. They weren't worried at all. You'll learn. It'll be hard, but there are so many like online resources and like people in the research group to help you out with that. So for me, it was definitely it was a big learning curve. But oh my gosh, I've learned so much about not about chemistry at all in my chemistry so far. I've learned a lot of chemistry too, but
when I was an undergrad in chemical engineering, I knew I wouldn't want to go to the industry. So I saw all my friends that were preparing to go to industry, to work in industry, but I want to do some research. But I also didn't know what I want. So when I saw the opportunity of working with computational chemistry, which involved computation, physics, mathematical models, biology, and chemistry, so it attracted my attention. So when I was in the second year of my undergrad, I started working with computational chemistry at university.
Well, so what would you say is like a big, like maybe one big pro and like one big con of working in the field? Not really doing lab work, like do you see that as like an advantage or a disadvantage? Do you get jealous of people going to do lab work, or or is it just a different way of doing things?
I think this is a great question. One of the big pros of computational chemistry is you can work from home. One of the big cons of computational chemistry is you can work from home. So I think it's great to be able to like just quickly log on a cluster and just check on your jobs or like set up an info file and do it overnight. That's like one of the great things. You can work from pretty much anywhere. If you're sick and got to stay home, or the world is falling apart and there's a pandemic going on, you can still be productive. You can still get some results in and get that done. I do really miss working like in a glove box. And I mean, granted, I may have the opportunity to do that in the future, but it is really nice and all that. But on the other hand, you don't have to worry so much about safety training, about having to be trained on specific things, having to take safety things every year. So it's a lot in terms of like, the equipment you need and the training you need. It's simpler, but it's like it's more just a pick your battles thing. Some people are going to find it easier. Some people find it harder. Some people like both.
So I didn't have to go to the lab, but I still could produce a lot during the quarantine stuff. So yeah, that's a good pro. I guess the cons is also you can work from home. So
I'd say like one pro is you learn so many skills that are translatable to so many different areas outside of chemistry. Like I know people with chemistry PhDs end up going into like finance and like working like Wall Street or like those sorts of things. And like I think like physical chemistry in general, like a big component is just being able to like mathematically model things and like think about things like in very mathy kind of ways. And so like that is a skill that a lot of like companies are really attracted to. So I think that's a big pro. A big con is like sitting at a computer all day. It's so horrible. I have back problems because of it, but like it's not helping. And so my research group, like we started doing like daily or like once a week, like yoga stretch sessions, like in the early afternoon. Be like, all right, let's go to the conference room and stretch, like get up and move around. And in my other research group, we would do like coffee dates where like every single day at 2 p.m. we would get up and like walk to go get coffee just to make sure that we like go longer than just to like go to the bathroom or refill our water bottles.
Yeah.
Right.
I think
Yeah.
What do you guys want to do after you're done with your PhD?
The
that's a
question.
good question. I know for sure I love teaching. I mean, I thought I'd enjoy teaching when I got here and became a TA. And so far I've been proven right. I actually really do love that. So I definitely I do want to see myself in academia. I do want to look at into teaching and stuff. And I mean research as well. I mean, but I think that it's really nice being able, one of my favorite things, and something that's actually kind of been dulled by the pandemic, is just being able to go into class and see a fresh batch of students ready to learn organic chemistry, or maybe they're probably thinking about other things,
You get ready to crush their dreams. Yeah.
Yes. Well, not really. I try to be as helpful to them as possible. Try to remind them that, of course, grad school is always an option, and it's actually in some senses, it may be easier than you realize to if it's something that you want to do. You don't have to have the most stellar GPA or most perfect resume to get into grad school. And I mean, I'm here and I'm on my way to get a PhD. And if I can, I'm sure a lot of other people can.
I was expecting to win the lottery when I finished the PhD, but I'm not so sure. I hope I continue doing some research. The pandemic has shown the potential that how science is required to the world today. So yes, I hope to contribute somehow in the field of protein engineering or in the field of computational chemistry at all.
I was gonna say I've also see myself kind of going the teaching route, but ideally it would be academia, but I don't know, academia can be a really hostile kind of place. So it definitely depends on what institutions are hiring at the time and kind of how their chemistry department feels. CSU is great, by the way. I'm not, it's not about,
Yeah.
I feel academia in general, can be kind of a big shark tank, and I don't like that very much. And so I'm open to the idea of working at some sort of biotech company where it's a lot kind of more friendly, and just the environment is a little bit better to work in. But then also I'd want to have some sort of mentorship acts at part to that.
This is the prediction question. So where do you see the field in 10 years? The question arises because say someone's watching this on Twitch or YouTube and they're, say just finishing high school now, and then, maybe they're watching this in a couple of years time and they're just finished high school and then they'll do it. So that it's very well, people could be watching this and then be entering this field in 10 years time. What do you expect they will be doing that's different to what you're doing currently? What do you expect the routine sort of person will be doing? Is it doing the same things? It's just everything, it only takes 1 week to do a microsecond, or is it going to be quite fundamentally different?
Yeah, that's actually a really interesting question, because I don't really see the workflow for computational chemists changing much in 10 years. I mean, things might become more accessible, in terms of, having graphical front ends for things that usually you'd only deal with in the terminal. Things will become more straightforward to work with, just general people will make easier tools to work with things. But one of the things that I'll make this wild prediction.
Yeah, good. Wild predictions.
In terms of hardware, Moore's law is running out. You can see all these different, Intel's suffering right now and trying to do 10 nanometer plus.
Yeah.
And I mean, and there's a limit to how small we can shrink processors. And we're coming up with that limit very soon. The thing that I'm personally kind of expecting to see is the rise of application-specific integrated circuits in computational chemistry. That instead of working with general-purpose hardware, just general-purpose CPUs and stuff, we'll start making hardware that is specific to the kinds of problems that we want to solve, so that we can solve them faster. Because it'll cost a lot more to do so. But imagine having a processor that's just designed to run DFT, or at least very optimized to do DFT, versus what we have, which is designed to do a lot of different tasks at once. So that's my wild prediction for where we'll be in 10 years.
That's a good prediction, because we're already kind of seeing that happen with D.E. Shaw's research group. So D.E. Shaw is this sort of investment guy. He was in the finance world, and then he kind of shifted and went and decided he wanted to start funding chemical research. And so he has this supercomputer that was designed to run molecular dynamics simulations. It's called Anton, and it's just really well equipped to do that job. I haven't heard about many other groups doing that, but yeah, I could definitely see it going that direction.
So I'm positive that the advances on computational hardware and computational implementations of softwares, they can speed up simulations, and we can simulate larger systems. We can simulate systems with at a more detailed perspective. So yes, I guess that in the 10 years, we have seen, 10 years ago, there are some simulations that we can perform today that 10 years ago couldn't be done. So yes, I guess that in the next 10 years, you can see the growth of computational possibilities of systems you can simulate. And of course, you can make this more accessible, simulations more affordable,
No one said quantum computers. That's is it still? I still think it's a little bit of conspiracy. I suppose 10 years is too soon. But you know, someone could be watching a YouTube video on a quantum computer. With this 10 years.
Possibly. I mean, it's hard to say because it's not like we really see, like, we don't see quantum computers in consumer hands, and the limitations and where things need to develop are going to be a little, like, we can get, like, from the data set of everyone out there just using a regular old computer, we have a lot of information for how we can improve our hardware and stuff. And that's something that I guess haven't thought about. There are certain algorithms that are much faster if we use them in a quantum computer. The only thing that comes to mind for me is like integer factorization, but I'm sure there are plenty that will actually be more, like, they'll be easier to run or faster to run on a quantum computer. The reason, by the way, I made the ASIC prediction is because we're already kind of seeing that in processors. Like, we're seeing that we have dedicated GPUs, dedicated machine learning hardware on consumer grade computers. So I think this is something that we'll probably specialize in a lot more, and possibly even the quantum realm, though I'm not really sure how that would go.
What about machine learning?
Machine. Okay, we'll ask about machine learning.
What about machine learning in the future? How do you expect it to play a bigger role in computational chemistry, or?
Absolutely, yeah. I think machine learning, like almost every computational group now, is like, machine learning? Oh, I should start doing that. Whether they like really have the means to or not, but it's that's definitely, I think, like here to stay in computational chemistry. But what kind of goes hand in hand with that is open source data. Like, we, as computational chemists, we are obtaining so much data, like just from molecular dynamics simulation, I have like terabytes and terabytes of data that will never be used. But we don't have like some sort of like open source, like platform where you just kind of like put all your data there just in case somebody else was interested in running a 1 microsecond trajectory of IGPS. Like, you might want to access some data that I didn't really care about, but I still had, things like that. And that's really like, in order to like have machine learning continue to grow, we need like all of the data that is being obtained, like, needs to be accessible to other people to then be able to use in order to train machine learning models and do things like that. And so I think that's kind of like the limiting factor for machine learning growth in computational chemistry, is just the accessibility of huge sets of data to be able to build these models and train them.
So the question about computation, it seems like, the work is so limited by the amount of like power you have computationally. Say, next week computers got infinitely faster. What if we replace the silicon with germanium? Now look, they run, whatever. Like, what can you see computational chemistry doing if there weren't such hardware limits? Does that make sense? So it's probably too. I mean, you probably could do everything then. But you say, is there, like, if you woke up tomorrow and computers were, 1 billion times faster, what would change about the research, do you think?
Talking about proteins, if you could use endless computational resources to do some protein research, we actually could enhance our predictability of protein sequences, protein structure, three-dimensional protein structures. And from this perspective, from this point of view, we could engineer novel proteins to target these proteins, we could engineer novel drugs, we could, I guess it would be a real breakthrough in medical science, since you could engineer protein for anything you want. And you could even simulate a human cell if you had like endless resource.
Right, yeah. Yeah, because because theoretically you could simulate something, as big as a cell if you had the computational power, but it's just like that would take in current methods like forever. But the models are actually reasonably good at predicting that if you had infinite power, maybe.
It doesn't work if you have endless computational resource, but you don't have a good model. If
Yeah.
you can't describe the model accurately, then you can have any computational resource you won't have good results. So they must go together. You must have computational resource, but also must have good models.
I hope tomorrow that computers are billions of times faster.
Me too. Maybe it can actually run Zoom without stuttering.
Yeah, maybe.
That'd be pretty nice.
Yeah, Minecraft on max settings. That's what I want.
Yes, Minecraft with RTX. I want to try that someday. Oh man, yeah. I think actually, just to answer that question, I think when you start not having limits in terms of processing power, your limit then becomes the coder. A lot of it is going to be like, how fast can you fix bugs in your program, or how can you improve your processes? And I guess at that point, algorithm improvement would be an issue. It would be a lot of bug fixes, usability. If that was a factor, I would love to be able to one thing that I've thought of doing myself is actually starting to put together a cluster, just not even out of particularly powerful hardware, just like Raspberry Pis or something very small, and be able to do my own computations at some point. I think that would be one of the big things that would be, I got into chemistry because I was able to mess around with chemicals as a young person. And I feel like being able to explore properties of materials, explore structural chemistry, and do that stuff at your own home will be one of the best possible things could ever happen in the field. We have a bunch of young, very motivated, and already very experienced young chemists ready to produce results and get published.
That's what you want. People coming in with results already.
Yes.
The perfect students.
Yes. There actually is one question from the chat that I find very interesting, and I feel like this is less applicable to me. Yeah, I'm checking chat as well. But I think this is a great question, mostly for the other two guests, because I feel like for us, we trust our computational methods a lot. But how do you convince experimental chemists that computational chemistry, these models, are can be trusted? Or
can we trust you? No,
Best and worst question. Really, to answer that, my initial response is oh well, I used this density functional because I know that it works well with these sort of organic atoms and things like that. And of course I went through and I read the paper where they published what exactly this density functional entails, but I didn't actually do that work to build this functional. And so to me, it's if I were the one developing my model and then applying it to systems, I'd have so much better ability to be oh, just trust me, I did the work and I know this. But a lot of it is kind of the people doing the simulations. We put a lot of optimism into the people who built the models originally, and that they built it very steadily and with a lot of care and a lot of intentionality with it. And it's always going to come back to being able to validate your model with experimental results. We're going to be able to get past that. That's kind of going to be the hallmark of computational work. It'll be hard to find a computational paper that doesn't say, oh, and when compared to the expected value, we get reasonable results.
Is that frustrating to do every time you're writing a paper? You think, oh, I don't know, buddy, find someone who's done some experiments.
Yeah.
It's not frustrating, but I have to keep in mind that oh, this matters to compare.
Yeah.
Thank you.
That's all right.
Yes, thanks for hosting us.
Yep. Thanks for coming along. It's been very interesting.
I will just say, if you have any questions that were not answered here, feel free to send me a message on Twitter.
I'll link.
We'll link your Twitter.
Yeah. We'll link the Twitters, and people can get in touch if they're really interested in your research and cite your papers, etc. Yeah.
Yes.
That's what we want. All right. Well, I will end the stream, and thank you, everyone.
Thank you, guys.
enough.
Thank you for the opportunity to allow us to discuss our research work.